Today we have Arianna Jordan as Arianna after Bachelor's of Science at University. Was that the sum?
Yeah, that's amazing.
Oh, okay.
Yay.
So after her bachelor at San Jose, she got a master's from Howard University in atmospheric sciences in 2020. And she then joined OU as a PhD student, initially with TA, and moving on to funding related to the AWAKEN campaign. And so she's funded through a subcontract with Lawrence Livermore National Lab, and she will give us an update on the PhD research.
Okay. Thank you, Petra. Thank you, Tyler. And thank you all for sitting through that and coming here online and in person. I just realized, am I muted online? Okay, good. Okay, so I'm looking forward to share some of the findings that are very preliminary, but have come from the American Wake Experiment, or AWAKEN, a campaign where we're interested in looking into if wind farms are having effects on boundary layer features. But before getting into the nitty-gritty, I want to briefly start with the basics in case anyone here is not familiar. When we talk about the atmospheric boundary layer, we are referring to the lowest few kilometers of the atmosphere that have some kind of direct interaction with this Earth's surface, for example, rain or snow. And during the day, heating from the sun causes turbulent mixing in this layer, which is why we usually call the boundary layer during the day the convective mixed layer. And when the sun sets, that thermally driven mixing begins to subside, and then it turns into what's called the stable boundary layer, where the previous day's mixing becomes detached from the surface and ends up as the residual layer above it. And then as the sun rises, the stable air shifts into this entrainment zone up here, while thermal heating takes place again, and the cycle starts again. So given that a lot of meteorological processes occur in the boundary layer, it's necessary to understand as much as possible we can about it because it has direct ties to other areas of meteorology, like forecasting, severe weather or otherwise, modeling, and air quality. And we as humans live in the boundary layer, so whatever happens in it affects us as well. So with that in mind, allow me to introduce the American Wake Experiment. In short, AWAKEN is a collaborative field campaign that has the intent of using observations to validate wind turbine wakes. And understanding these can help in designing wind farms in the future to help with more power production and lower energy costs. Specifically for the purposes of OU and our close collaborator, Lawrence Livermore National Laboratories, the AWAKEN project allows the opportunity to research the impacts of wind farms on boundary layer features. And that's useful because many of the wind farms that occur in the AWAKEN domain have only recently been built there. As you can see from this little visual here, it loops throughout time. You can see that there's no wind farms until it gets to around 2010s or so. Then they start building up. So we don't really know the differences that that's causing in this area for some of those important applications that were mentioned, like forecasting and modeling. So that's where we can really get some of that useful information. AWAKEN has been going on since 2022, and several of those involved plan to be up there until 2024. And it takes place in the Southern Great Plains near the Atmospheric Radiation Measurement Site, or ARM. That's where their central facility and a bunch of their extended sites are. And ARM has a bunch of meteorological instruments that continuously measure conditions in the Southern Great Plains. So they're another source of data for this area. Okay, so looking at our contribution to AWAKEN from the OU side, if we want to study boundary layer features, there's a few different types of instruments we have to do that. Here, we have our own platform containing such instruments that's called the Collaborative Lower Atmospheric Mobile Profiling System, or CLAMPS. We actually have two of them, CLAMPS 1 and CLAMPS 2, and here's a picture of one of them, but they both have the same capabilities, where you'll see they contain an infrared spectral radiometer to gather thermodynamic measurements, a LiDAR for kinematic measurements, and a microwave radiometer along with a tower to get both thermodynamic and kinematic variables. So with that in mind, let's go back to our boundary layer visualization. And I want to just focus on the nighttime into early morning period, because during that time is where we receive one particular boundary layer feature in the Southern Great Plains called the nocturnal low-level jet. This is just an increased area of wind speed in the lowest kilometers of the vertical atmosphere that occurs overnight. And here's an example of what that visually looks like from time height cross sections of clamps data, and the heights are aligned to match the heights of this figure. So this in particular is a strong nocturnal low-level jet case where it has a very well-defined nose, which is just areas in the jet that have the highest wind speed. Now, because low-level jets occur very often in the overnight in the Southern Great Plains, and because there's still a lot that we're learning about it in terms of how it changes in time and space and often increases atmospheric mixing, you can imagine that it's a big topic during AWAKEN that we really want to research during this project. And as seen here, our LiDARs have that capability. Well, there's actually been some AWAKEN analysis done already on low-level jets from other entities involved in the project. Specifically, this is an automated nocturnal low-level jet classification algorithm that was developed as a way to group the nocturnal low-level jets based on their strength. This was done by a group at the National Renewable Energy Laboratory and CU Boulder. And there's been various work on classifying jets before doing this, but this one in particular mirrors the paper from Van der Wende et al. 2015, where we're grouping the jets into 4 categories based on the maximum wind speed and if there's shear above the nose of the jet. And then all other cases are classified as no nocturnal low-level jet observed. So this classification algorithm was used for a few different AWAKEN sites where other instruments have been deployed, but there's an AWAKEN site called A1 that will be the focus for this presentation because it's not far from where one of our clamp sites was deployed. So getting into that, we'll start with where clamps was deployed. Clamps 1 was at a golf course that ended up being a pretty good spot surrounded by wind turbines to measure their potential influence on the boundary layer. But to do that, we need to have observations outside of wind turbines as well to compare. So Clamps 2 was placed much farther away from any of the wind farms. And our considerations for picking this site are listed here. But then we have the site A1, that's the site that's used to classify the nocturnal low-level jets. It's relatively close to where Clamps 1 is stationed. It's only about 7 kilometers away. And the station is also surrounded by wind turbines. Well, at least from the north, it's placed right in front of one, as you can see from this picture. So I'm including site 8.1 here because the desire was to take the existing algorithm at A1 and apply it to Clamps 1 and Clamps 2 data to see how it all compares. So that algorithm was shared with us and we could apply it to our clamp systems. And the low-level jets were classified in the same way as at A1 to help answer the question, do the nocturnal low-level jet classes match between sites A1, C1, and Clamps 2, C2? It's hypothesized that because the nocturnal low-level jet changes in time and space, that there are some expected differences between the sites, especially from between A1 and Clamps 2, because Clamps 2 is located much further south. So with that said, only the LiDAR measurements are focused on for this talk. Information on the LiDARs for each site is at site A1, they had an arm scanning LiDAR where it collects kinematic information at 20-minute time resolution using conical BAD scans. And our clamps LiDARs overall measured 10-minute scans, but there were a couple cases that are included here where the resolution is a little bit different. So the cases were matched to the nearest A1 timestamp. More information about the cases chosen. They were chosen for the summer of 2023, that campaign, during the 0 to 16 UTC time period, so just that nocturnal and early morning period. They are based on the criteria from site A1 measured, so I picked when A1 measured the nocturnal low-level jets for for the following cases, class 1s and class 3, and as well as when there was no nocturnal low-level jet observed. So I chose 5 cases from each of these categories. And also the cases that I chose were ideal, so we didn't want any data outages or any rain. And also the cases that were chosen were only for when the highest class was measured, when it was also the most frequent. So for example, if the highest class measured was 3 at one point, but it's mostly class 2s, that case wasn't picked as a class 3. We wanted to represent as much as possible of the nocturnal period, so we chose the highest and most frequent class. But as it turns out, during the no nocturnal low-level jet grouping, it was hard to find cases where there wasn't any nocturnal low-level jet. So the only exception to this is 2 of the 5 cases in this category where there was a couple of class 0 assignments. But otherwise, the majority of it does represent no nocturnal low-level jet observed. Yeah. All right, so once we have the classes assigned and we get an idea of what the data sets look like between sites, we can look into not only what the influence of the nocturnal low-level jet does, but also the turbines on another boundary layer feature, atmospheric mixing. So based on both the class of the jet and if turbines are in the vicinity, the question I have here is, does strong near-surface mixing coincide with strong nocturnal low-level jets? And if it does, is this further enhanced by wind turbines? So the algorithm used at A1 doesn't just provide low-level jet class cases, but it also measures other quantities of insurance. For example, one of those being rotor averaged vertical velocity variance. We have the capabilities of computing vertical velocity variance from clamps as well. So we view the mixing from all the sites if that's being impacted by the class of the nocturnal low-level jet. So that's what's done here using the Nationl method at 10-minute windows to match the time resolution. And we averaged, and the heights were averaged from the rotors, from the rotor regions. So we're just considering the heights from about 150 meters to 25 for the turbine in front of A1. However, the lowest viable measurements from the lidars start only at about 60 meters. So it's realistically, we're not able to get the very bottom reach of the rotor regions. So it's more about 60 to the highest clamps available height around 150 meters, I believe 155 or so. So we're averaging the heights of that rotor region to get the vertical velocity variance. Okay, so jumping into what are very preliminary findings, we can start by answering the first question: does the class or strength of the nocturnal low-level low-level jet change between sites? And we can start by comparing clamps 1 with the lidar collections at A1. So here I compare by showing the difference in the jet classes between these sites throughout the nighttime. To clarify how that's shown, anywhere there's completely blank spaces means that neither site measured a nocturnal low-level jet, so they're agreeing in that sense. Anytime there's these dark green spaces, both sites measured a nocturnal low-level jet in the same class, so the difference would be around 0. Where they disagree is if only one site measures a nocturnal low-level jet, which is listed as either A1 or C1, depending on which one measures it, or if they have a difference between classes. So if the value is 1, 2, or 3, that's not these dark green values. And here I have the cases separated by what was originally identified at site A1, except for these couple of times here that on the 31st and 7th, where A1 did have class 0 a few times, because like I mentioned, it was hard to find all no nocturnal low-level jet cases. So otherwise, though, for the no nocturnal low-level jet group, mostly they agree, the clamps 1 and clamp A1 lidars agree pretty well with each other. There are a few times where a jet was measured on some points, especially for 916, and that's a case we'll come back to, so remember that. But overall, it does pretty well in agreement in saying that neither site measures a nocturnal low-level jet. Going to the class 1 cases, these 5 cases here, it also does really well in measuring in agreeing between a nocturnal low-level jet between clamps 1 and A1 without a huge difference value between them. There are a few points where it goes to a difference in class of 1, but overall it does a pretty good job except for those few points and a couple of points near the beginning and ends of periods where jets are measured at only one site. Where there's strong disagreement is in the class 3 cases, where either one site measures a lot of a nocturnal low-level jet while another doesn't, or the difference values are pretty big in this case. So class 3, when the strongest nocturnal low-level jets happen, is where the most of those differences occur. So that was for clamps 1, comparing to A1. Now comparing clamps 2 to A1, which is a further distance south. I have a little schematic here to show the distances. Here, there's more times when C2 measured a nocturnal low-level jet during the times that A1 didn't in this class of no nocturnal low-level jet grouping. So it's about half of the time when it does agree in these groups and half the time where it doesn't, depending on the day. It seems to occur more like towards the early morning hours for this grouping though. Class 1 is pretty similar to the last schematic where we compared clamps 1 and A1, but there are a few more difference values where they're a little more different rather than matching exactly. And then class 3 does even worse than before, where there's a lot of times that only one site measured the nocturnal low-level jet. Specifically on 9/23, it's like all A1 throughout the whole entire night, but clamps 2 didn't measure that. And then looking at the comparison between the 2 clamps instruments. So now we have similar instrument setups that we're comparing along with similar time resolutions for not all, but the majority of the cases. In the known jet group, there still is some disagreement. And so that's going back to the distance between them. And in the class 1 group, it's looking pretty similar to what it did before when comparing C2 and A1. So there are areas of disagreement, but it's not as, but it has that agreement that C2 and A1 had. So at least that distance is consistent. And looking at class 3, it's also very bad for between clamps 1 and clamps 2, where a lot of the time only one nocturnal low-level jet, only one site measured it. And where they both measure it, they do a little bit better between the difference values, but it's still a lot of differences between the sites. So to visualize what the different nocturnal low-level jet classes look like, here's the measured wind speed of the low-level jet nose. So we're excluding the group with no jets observed and just focusing on class 1 and class 3. Class 1 is this top panel, class 3 is this middle, and then at the bottom is the averages between the two. And at all sites, the class 3 jets are yielding much higher maximum wind speeds as we'd expect them to. And yeah, it's doing what we would expect. And we are seeing some differences between the C1 and A1. I'm just realizing that that's because this was plotted before the times were matched. So the resolution's a little different here, but overall the message is the same, that the class 3 is much higher in wind speed. So that's checking out. But now let's transition into looking at the mixing. So we're back to adding the cases that have no nocturnal low-level jet, which is this top panel. Class 1 is the middle panel, and class 3 is the one below that, and then their averages are at the bottom. So at all the sites, the class 3 yields the strongest mixing. It's less obvious at clamps 2, where the mixing isn't strong from any of the cases. But it occurs judging just by the end of the period, where the average mixing is higher at clamps 3 going into the going into the daytime boundary layer. But on average, everywhere else is consistently overnight with this red line being the highest from class 3. Going back to looking at clamps 2, so that's the site where there's not much of a turbine influence, we're seeing there's not much mixing overnight. And so it does look like that the wind turbines are having at least a little bit of an effect on the sample size of these cases. So one case I wanted to draw your attention to was the September 16th case I mentioned a while back. That's this green line here, where it does have a little bit more mixing than the rest of the class. This is supposed to say no nocturnal low-level jet cases. That's what this panel is, but it has more mixing than those areas. And so just looking at an example of our clamps data, here's C1 vertical velocity. You can see that there is quite a bit of turbulence going on in the atmosphere overnight. That's not necessarily, there's a little bit of mixing near the bottom, but particularly these streaks are of interest because that kind of tells us what the atmosphere is doing. And if you go back a day or earlier in the day, you can see that right before this 0Z period started, there was huge downdrafts that occurred, and that coincides with a rainy period. So even though we didn't measure rain into this 16th 0Z to 16Z case, the atmosphere was still very turbulent. And so it's not, even though there wasn't rain, it's not necessarily an ideal case in this sense, but that's why the mixing is a lot greater for there. So this is something you can visually see in the clamps data as well, the mixing differences. For example, here is a no nocturnal low-level jet case, one of the example cases that I used, where you don't see any mixing in the atmosphere coinciding with not much of a low-level jet, maybe a little bit of wind speeds here. But overall, it's pretty calm in the vertical velocity. So vertical velocity is what's used to compute the variance. Just a quick note, our clamps 1 wind direction has been wonky in its directions throughout the summer because our azimuthal encoder has been not working properly. So these values are estimated from a site really close to clamps 1, just to the southeast of it, about 2 kilometers. It's site C1A. The rest of the variables are fine, but I wanted to make that note real quick. These are just estimated values. But anyway, going into a class 1 case example. So here we have a little bit more of a nocturnal low-level jet, and you can see that visually. But we have a little more mixing occurring at near the surface of the atmosphere, particularly in clamps 1, where the wind turbine region is. And we don't see that mixing so much where the wind turbines are not influencing clamps 2. And then looking at a class 3 case, here's 925, where it has a really strong nocturnal low-level jet. You can really see the mixing in the clamps 1 near the surface, especially where the rotor heights region is. And you can kind of see it in clamps 2 in this case as well, but it's not as intense except maybe in some areas. Generally though, clamps 1 has the stronger mixing between the two, even in the strong nocturnal low-level jet cases. So going back to these questions, does the nocturnal low-level jet class match between A1, C1, and C2? Somewhat. It depends on the grouping. There's mixed results between the no jet group. And that's sensible when you consider how few cases actually had no nocturnal low-level jet. That was pretty hard to find. So you can imagine if that's hard to find from one site, probably other sites are going to have cases where they're measuring it as well. Class 3 had the best agreement of all the sites. I assume because it's not restricted by those conditions that I'm just mentioning. And then class 3 had the worst agreement between all the sites because stronger nocturnal low-level jets are more likely to have that variation in shape and size and duration. And so it's more likely that that's going to vary across space and time. Now, it is hard to quantify how much of this is due to low level jet variation and how much is just a result of different instruments, slightly different time resolutions, or other factors. But overall, the results are what is expected. Onto the second question, does stronger mixing coincide with a stronger nocturnal low level jet? In these cases, sorry, I'm not sick, I promise. It's a lingering cough. In these cases, the vertical velocity variance from class 3 was the strongest out of the 3 groups from at all 3 sites. And this occurs even though there is the occasional differences in the nocturnal low-level jets from each of the classes. The class 1 and no jet groups are kind of interchangeable in their mixing. It's very slight differences, but definitely the class 3 had more intense. So for at least this small sample size, I answered this as yes. And then if so, is this further enhanced by wind turbines? And so even with the no jet group, there was on average higher vertical velocity variance at C1, which is surrounded by the wind turbines, and A1, than at clamps 2. So you can visually see that too in the clamps data that was just shown for all the sites, or for the clamp sites. So these mixing questions do match what was found from previous literature, which is good. But there's still plenty of other things that can be done going forward to make this analysis stronger. So we just wrapped up getting our completed clamps data, at least from clamps 1. Clamps 2 is still deployed out there. We'll be grabbing that pretty soon. But we were only deployed for AWAKEN for about a year or so, and while other entities are continuing into 2024. So we just kind of got this data and was able to add a little bit of preliminary analysis to it, but there's still plenty more to do, such as if I want to continue this in particular, increasing the sample size with more cases, classifying the jet in other ways, such as the shape, the magnitude, the duration, looking at wind direction impacts and classifying how the different wind directions may be playing a role, and also looking at potential wind farm impacts on the jet itself rather than just the mixing. Or going forward into other topics to look at the turbine impact, looking at wind turbine impacts also on convection, stability, morning to daytime and evening to afternoon transitional periods of the boundary layer, as well as exploring historical data sets from the ARM. We have the label campaign that has historical data that was around 2012, 2013, from before the turbines were built. So that would be a very good comparison to be able to do. But for now, that's all I have, and I will happily take any questions.
Thank you.
Yes.
So you had the classification of the jets based on the speed and also shear.
Yes.
What was the depth of the stop?
Wherever the max wind speed was.
But then the second level, how high did you go to evaluate the shear above them?
Oh, shear above the nose. That was done just when, so whenever the max wind speed was identified, it was just right above the max wind speed. So the data point above that.
So did they
But that's the in terms of how much above.
Yeah, I see what you're saying. I have to review that, but I believe it's just as soon as, yeah, I believe it's just directly after, and I'll have to review that. I'll get back to you on that.
Any other questions? I guess I had a follow-up question. Since there are 2 criteria, let's say the maximum wind speed is reached, but the shear does Just threshold.
Yeah.
Yes, threshold. It's not complete. It's not reached. How would a jet would be classified? Let's say in class 3, the wind speed is over 20 meters per second, but shear above the nose is less than.
Yeah, then it doesn't count as the class 3 in that case.
Do you have any sense of how many cases met one of the two criteria but not the other one?
Looking through, there were quite a few class 3 cases where you would expect to see the class 3 cases. So I feel like for that example, for class 3, for example, it was able to match that quite a bit because you have that very defined nocturnal low level jet that where the shear does have that difference. So I think for most of the cases, it did keep that condition, but I would have to actually quantify to know for sure.
So it could be that the mean wind speed and the wind speed criterion was met at both cases, but shear criterion might maybe not. Because of that, it would be differently classified.
Yeah.
Okay. Any other questions?
Yes.
And ask a follow-up question to my first.
Yeah.
So you had a picture, I think it was like a C1 and C2. C like Earth coverage and starts setting off. And I forgot which slide it was.
Oh.
Yeah, it was toward the end. Again, like side by side.
That timelines cross section.
Yeah.
Mhm.
That's 30.
An hour.
Well, actually, the way you do it. Oh yeah, this one here. No, so the one before, I think, let's see. C1.
Oh, okay.
Yeah. So, so the data looks like it's kind of cutting off at different. Is that a meteorological thing or the clamp slightly different so that extent that your sample could clamp slightly?
Yeah, so both A1 and the clamp system, I only measured up past 60 meters or so.
So he's talking about the top layer, why
Oh.
see data.
Oh, okay. Yeah, okay, so that's due to the way it's filtered. So this applies a traditional SNR filtering method, and the threshold used for here was about 1.01 or so. And so, yeah, we start to lose the data around here, but a lot of the rest of this would just be noise that's filtered out by that SNR method. And so to get an even clearer picture of that contains all the data while still filtering the noise, right now we're working on implementing a window E algorithm that's been developed by Josh Gebauer, and he's been helping and to filter it in a way where we're still keeping that data, but still losing, but still taking out the noise.
Is the C1 seem to be the same way? So filtering is out.
The window E is, but the filtering is actually different because the C1 has had different technical issues, and when it came back, it was the noise filter was different.
It's the same.
Yeah. Yeah.
So there are differences of the data that can play a role. But, yeah.
So that would be beautiful.
But I mean, the differences are not in terms of when we lose the data at the top. I would say that in these two examples, they're not really huge differences.
Yeah.
When we mostly measure noise. So I would say the aerosol content probably wasn't very different to.
We get some differences.
Mhm.
I think I'm getting back to my question about here. Depending upon where how high you go, depending on the definition. Yeah, how big. Sure.
Mhm.
One could possibly get that shear view.
Yeah.
Yeah. Yeah, that's very true.
Yeah, actually, depending on how that so we only got that code from Julie Lundquist very recently. We have to predict
Mhm.
how they apply that shear criteria. It is given how quickly we lose data, it is not trivial to get good estimate of the shear about the jet.
That would be suspicious.
Yeah.
Yeah.
It's calculate that, it's go up.
Yes,
It's about your-
yes, we can.
Yeah.
We can come up with our own classification.
Yeah.
Yeah, there's lots of different ways to classify the data. This is just what they were using to compare for the purposes of AWAKEN. So. Yes.
Do you notice any difference in the typing of global jet claims to versus either?
A little bit. There were very slight differences, both just looking at the data and computing it. The duration would change occasionally, and that's why that's something I really want to look into. Is like with these changes in time and space, how is the start of the jet changing from one place to another? And that's a really that's something I did see a bit here. So that's another instance of where those differences play a role in between sites. But yeah, that's something to definitely dig more into. I think the duration is a really important factor because it also plays a role into how the nocturnal low-level jet is around the wind farms and at the specific sites. So yeah.
Yeah, other questions? Okay, then let's find out we have all one more time.